This lesson is a continuance from the Introduction to Simpson's Rule lesson. So what we're looking at in this lesson is working through a couple of examples so that we can understand and use this rule fluently. So at the start, we will review Simpson's rule. Obviously, it is an approximation of area under a curve, or approximate area, particularly when we're looking at curved sections. All right, so we have our width divided by 3. W stands for width. This is our start point and our end point, and all of the odd subsections are multiplied by 4. Even all of the even are multiplied by 2. If we're taking this approach, we have to be very careful to make sure that the start point is x0 and not x1. If that's the case, then it's quite easy to apply. Now, interestingly enough, the two scenarios where Simpson's rule will not be approximate and will be exact is when we're looking at finding the area under a parabola, because it is based on a parabolic subsection or a cubic function. All right, so our first example is a cubic section. And so that means when I'm thinking about how many parts I'm going to break this into, I'm going to take the simplest approach, and I will break this into just 2 sections. 2 sections because that will make it easiest. So I'm looking at this x cubed, and I'm trying to find the area between 2 and 5. And because I'm only breaking into 3 sections, that middle point will be 3.5. So that means I'm only looking at x0, x1, and x2. So x0 is 2, x1 is 3.5, and x2 is 5. Our width, which is b take a over 2, will be 5 take 2 on 2. So width will be 3 on 2, or 1.5. And we'll need, obviously, f of x0, which is 2 cubed, which is 8. We'll need f of x1, which is 2 plus 3 on 2, so 3.5, or 7 on 2 cubed, and that will make it 343 on 8, and f of x2, which will be 5 cubed, and that is 125. All right, so our area will approximately be W on 3, f of x0 plus 4 times f of x1 plus f of x2. So there was no even sections. There was only one middle section. And so that means we've got our width, which is 3 on 2. So 3 on 2 on 3 is just 1/2. F of x0 is 8. We have 4 times 343 on 8, which will end up just being 343 on 2, and then we have 125. So when we put this in, we end up with an exact area in this case, but we'll still leave that approximate sign there. It's 152.25 units squared. All right, so nice and simple. That's Simpson's rule. When we know it's going to be quite accurate, we're only going to split it into those 2 sections. So the 2 ends and that middle. So next one, we're using Simpson's rule to estimate the integral between 1 and 0 of e to the power of x. So this time I'm going to break it up into 4 sections. We're looking at an exponential, and we're looking between 0 and 1. So if we split into 2 parabolic subsections, so section 1 between 0 and 1/2, section 2 between 1/2 and 1. So that means we end up with 1, 2, 3, 4, 5 values and 4 sections. So n is equal to 4. We'll have to look at f of x0, f of x1, x2, x3, and f of x4, where x0 and x4 are the endpoints. So f of x0, e to the power of 0 is 1. We've got e to the power of 1/4, so e to the power of 0.25, e to the power of 0.5, e to the power of 0.75, then e to the power of 1. All right, so calculating out this area, or approximating this area, it makes sense that we should know what our width is. So width is b take a on the number of sections. So that is, we have 1 take 0 on 4, and we end up with 0.25, or 1/4 as our width. So we have here width on 3, f of x0 plus 2 times our even value, which is f of x2, and then we have 4 times the sum of our odd values, which is f of x1 and f of x3. We then have our endpoint, which is f of x4. So when we put this all in, we've got 1/4 of 1/3, which is 1/12. f of x0 is 1. We've got 2 multiplied by e to the power of 0.5. 4 multiplied by e to the power of 0.25 and e to the power of 0.75, and then we have e to the power of 1. So this calculates out to be approximately 1.718 units squared. Okay, so nice and simple. Area between 0 and 1 of the exponential function broken into 4 sections, or 2 parabolic sections. We can see that our area is approximately 1.718 units squared. So we'll now look at another example. This time we're just using it to approximate an area. So a road is to be built by cutting through a hillside as shown. So we've got this cross section, which is the hillside. The width of the cutting is 80 meters and has a depth of 50 meters. So that means it goes on like that for 50 meters. In the end, we're looking at our volume is that cross-sectional area multiplied by the depth, which in this case is 50. We want to determine the volume. So this is a nice little easy application. We can see that it's been broken into 8 sections. So our width is 10 meters. And these values here, these heights, represent our f of x0, f of x1, f of x2, and so on. Okay, so to speed this up, we know that these are our endpoints, so the first and the last value. Our sum of the odd sections will be 2 plus 6 plus 4 plus 2.5. So that means we've got 8 plus 4 is 12 and 14.5. The sum of those even subsections will be 4.5 and 5 and 3. So it means we end up with 12.5. And we can put that all in to approximate the cross-sectional area being width on 3, and we'll say that it's f of x0 plus 4 times the odd values plus 2 times the even values plus the end value, so f of x8 in this case. So we have 10 on 3, we have 0 plus 4 times 14.5 plus 2 times 12.5 plus our endpoint, where the height is also 0. And so that means our cross-sectional area works out to be approximately 830 on 3 units squared. And our volume, which will be approximately the cross-sectional area multiplied by that depth, which we said was 50, will be 830 on 3 multiplied by 50, and that will be approximately 13833.3 meters cubed. Okay, so we can see that's a pretty simple application using Simpson's rule to approximate a cross-sectional area and then finding the volume by multiplying by the depth. Okay, so that concludes the lesson. That's really how we use Simpson's rule. You'll see that we can apply it pretty easily, but we can also use it to approximate area under curves. Now, just think, where is this really useful? So this will be useful in scenarios where we don't have a function and we want to approximate an area based off heights in a curved section. Or 2, we have something that we can't integrate or is too complex to integrate, and we want to approximate the area under that more complex function. We can also do the same thing. All right, so thank you for listening. That concludes the lesson.